Welcome to The Explainer. Today, we're pulling back the curtain and cracking open the playbook on how world-class large language models are really built, from that very first strategic question all the way to a polished, fully functional AI assistant. So you might think the first step is jumping into the code, right? Well, actually, no. Before any of that, the most critical step is asking a really fundamental question. Should you even be training this model in the first place? This isn't just about whether it's technically possible. It's about making the absolute smartest use of your time, your money, and your resources. And honestly, as this decision tree shows, for a whole lot of people, the answer is a simple no. Look, if there's an existing open source model that can handle what you need, maybe with some clever prompting or a little bit of fine-tuning, that is almost always the smarter, faster, and cheaper path. Training a model from scratch should be your absolute last resort. But of course, sometimes you do have to build one from the ground up. It really boils down to three key reasons. First, you're doing pure research and trying to answer a very specific scientific question. Second, you have a production need that's either in a super specialized field or has really strict governance requirements. Or third, you see a real gap in the open source ecosystem and you've decided you're the one to fill it. Okay, so we've covered the why. Now, let's get into the how. Here's the roadmap for our journey today. We've just tackled that big to train or not to train question. Next, we're going to dive into designing the model's architecture. Then, we'll get into the incredibly important art of data curation. After that, we'll sweat through the grueling training marathon. And finally, we'll see how you take that raw model and polish it into a helpful assistant. Let's dive in. So, you've made the call. You're training a model. The first thing you need is an architectural blueprint. This is where you make the foundational decisions that will literally define how your model is going to think. Let's peek under the hood and see where a model's brainpower is actually located. It's pretty interesting. You can see that a massive chunk, about 65% of its parameters, are in what's called feed-forward networks. You can think of these as the model's raw computational horsepower. The next biggest piece, the attention layers, well, that's the magic that lets the model weigh the importance of different words and actually understand context. And speaking of context, a model has to know the order of words, right? Dog bites man is pretty different from man bites dog. One of the most popular techniques for this is called rotary position embedding, or ROPE. It's a really clever trick that encodes word order by, well, rotating their data representations. It's like giving each word a unique spin depending on its exact spot in the sentence. Now, here's a huge architectural fork in the road. Are you going to build a dense model where every single parameter gets used for every single token? Or will you build a mixture of experts, or MOE model? MOE models can be absolutely massive, but they only activate a small fraction of their specialized experts for any given task. This makes them way more efficient to run, even if their total parameter count is enormous. Okay, architecture set. Now we move on to what is, without a doubt, the single most critical ingredient in this entire process, and that is the data. I mean, this quote just says it all, doesn't it? Your architecture is how the model learns, but your data is what it learns. It dictates every piece of knowledge, every skill, and every bias your final model will have. And let me be clear, no amount of clever architecture can save you from a bad dataset. And here is a perfect, almost shocking illustration of how critical data decisions are. This is about the tokenizer, the tool that breaks text into pieces a model can digest. Just look at this. The exact same idea expressed in English takes 20 tokens. But in Arabic, it takes 122. That's more than 6 times the work. An inefficient tokenizer doesn't just cost you a fortune in compute, it actively hurts your model's performance. It's a huge deal. This reality has led to a major shift in how we think about feeding data to a model. The old way was just to create one giant, static mix of data and use it for the whole run. The modern approach is to create a dynamic curriculum. You actually change the data mix in stages, usually saving your absolute best, highest quality data for the very end. And the reason for that is simple. A model's final behavior is shaped most by the very last things it learns. Okay, blueprint, check. Data, check. Now the fun begins. We start the training marathon. And this is where all that clean, organized theory smacks right into the chaotic, messy reality of large-scale computing. And if there's one rule, one mantra to live by during this phase, it's this: be paranoid. I mean, truly, deeply paranoid. Every single tiny change, a minor code tweak, a software update, has to be tested relentlessly. because one little silent bug can creep in and completely corrupt a multi-million-dollar training run, and you might not even realize it for weeks. And even with all that paranoia, chaos still happens. Take this real-world story. A team launches a massive 11 trillion token training run, and right away, the speed just plummets. The immediate suspect, of course, is bad hardware. But after hours of debugging, they found the real culprit. It was a bug in the software data loader that just couldn't handle the sheer scale of the data index. A quick software fix, and they were back in business. But not before a lot of nail-biting. Another common nightmare is something called a loss spike. This is when the model suddenly starts making huge errors, basically unlearning everything it knows. It's terrifying. But these things aren't random. They can often be prevented with meticulous data filtering, like getting rid of super repetitive text and using some clever architectural tricks to keep all the complex math inside the model from blowing up. So after surviving weeks of training and processing trillions of tokens, you've done it. You have a powerful base model. It's brilliant at predicting the next word, but it's not yet a helpful assistant. For that, we need one last crucial phase, post-training. This final polish is a multi-step process. First comes supervised fine-tuning, or SFT. This is where you feed the model thousands of high-quality examples of instructions and perfect responses to teach it how to follow directions. After that, you move to preference optimization. This is where you teach the model what better actually means from a human perspective, usually by showing it two different responses and telling it which one we prefer. But wait, where do you get all that preference data? You can't just have humans do it all, it's too slow. So there are two pretty clever ways to scale it. The first is strong versus weak. It's simple. Get a stronger model and a weaker model to answer the same prompt, and just automatically label the stronger model's answer as the chosen one. The other method is on policy with grading. Here, you have the model you're currently training generate a few answers, and then you use another powerful model to act as a grader and rank them. It's more complex, but also more nuanced. So when you put this all together, the big takeaway is this. Creating a world-class LLM isn't some kind of magic. It's a disciplined, end-to-end engineering process. It's a systematic journey that goes from high-level strategic questions down to architectural blueprints to obsessive data curation through that intense training phase and all the way to that final, crucial refinement. You know, for a long time, this kind of knowledge felt like it was locked away inside a handful of giant tech labs. But that's changing fast. The playbook is opening up for everyone. So the only real question left is, now that you know how it's done, what are you going to build with it?